say that every natural number has a unique prime factorization. We can write a natural number as a factor of only prime numbers. This is the fundamental theorem of natural numbers. Application: give the prime factorization of each of the following number: 56, 56. We can start by dividing by the lowest prime number, 2. The quotient is 28. We can divide also by 2. The quotient is 14. We can also divide by 2, and the quotient is 7. 7 is a prime number. We can divide by 7. So 65, the prime factorization of 65 is this multiplication. 2 times 2 is 4, times 2 times 2 is 8. 8 times 7 is 65. We can write as in this by the power 2 to the third times 7 to the 1. This is the prime factorization of 68. You can do the same for the second number, 78. 78 is also an even number. We can start by 2. The quotient is 39. 39 now is an odd number, but we can divide by 3. The quotient is 13. 13 also is a prime number. So 78 equal 2 times 3 times 13. Each one to the first power. So this is the prime factorization of this number. You can't do the same thing with the rest of this list. Now we have a test of primality. How can we verify if n is a prime number or no? To prove that n is a prime number, we verify that not has any natural prime divisor, which verify this last condition with square less than n. If we can't find any prime number with square less than n, then we can say that n is a prime number. Why this? So let's n be a natural number, and his factorization is written as P1, P2, and so on, PQ. If n is a prime number, then n equal up a. For example, this factorization contains only one number. But if n contains more than one number, if n is not a prime number, we can write n in factorization, in this factorization. But for key, the number of factors, number of factors is the number of factors. No key is more than is greater than 2, because if q equal 1, then n is a prime number. We have two situations. If n is equal a p a times pa, some prime number as factor, pa times pa, then the two factors are equal, or we have pa and pj. In both cases, let's r equal a main pa and pj minimum. Then we can say that pi is less, r is less than pi. Then r pi pj is less than pa pj, which equal n. So we have also r square is less than rp j. Then r is less or equal than n. That is true for the number of factor equal 2. Is still true for if the number of factor is more than 2. For example, if we have 3 factor or more, n equal p1, p2, p3. So let's r the lowest factor, p1, p2 and p3, lowest of factor. Then we can write n as r times l, where l is the rest of factor. For example, if r equal p1, l equal p2 times p3, the remain factor. Then we can find this rating, and we can say that r is less than l because r is the minimum factor, and we can say that r square is less than rl, which equal n. So in each case we can find a prime number r with square less than n. If we find this number, this prime number, then if r exists, then r is a prime number, prime natural number with this condition. Then n is not a prime number. Else, if we can't find r, then n is a prime number. We can apply this test of primality for this application. Determine all prime number between 100 and 150. So we can test the primality for the first thin number 100, 100, 101, 102, 103, 105 and 9, 8. So the first number 100 is not a prime number because it's uneven. Also 102. There is here 104, not a prime number. 106 also, and 110 and 110 not a prime number. 105 not a prime number because the digit of unit is 5. For 101 is a prime number. The square root of 101 is about 10 and some fraction. So the prime numbers less than 10 are 2, 3, 5 and 7 because the next is 11. 11 is more than 10. So we can verify if one of those numbers divide 101. So 2 not a dividend because 101 is a odd number. 3 not a dividend because the sum of digits is 2, not a multiple of 3. The third 5 not a dividend because the unit digit is 1, not a multiple of 5. The last is 7. We can verify that. So 101 divided by 7 equal 14 and some fraction, so not a dividend. Then we can say that 101 is a prime number.